This looks like the solution matrix, I think, from that first problem. It might be that the columns are mixed up from what I had. I can't remember, but okay. So what can we say about the matrix exponential? First of all, example 1 here for the matrix exponential is a very fortunate event, right? If you take any of the other matrices we've looked at in the last series of examples and you try to calculate their power, just try to calculate the nth power of them, is it going to come out nicely? No, it will not. Like generally, if you just take a generic matrix and you try to calculate its nth power, it's really quite complicated. So this was rather fortunate, and this matrix was rather simple. So one of the things I would comment at the very outset is that direct calculation of the matrix exponential is very, very daunting. So its use is somewhat indirect, actually. So here are the properties of e to the, e to the m. So let's see, number 1, how about this? E to the 0 is what? It's I plus 0 plus 1/2 0 squared. In other words, I. So e to the 0 matrix is the identity matrix. Well, that's good. Also, number 2, if you have A times B is equal to B times A, two matrices, which commute, right? Then we have that e to the a times e to the b is e to the a plus b. Three. So since a times minus a is equal to minus a times a. In other words, the matrix commutes with its negative, right? We get laws of exponents in this case. So e to the a times e to the minus a is equal to e to the a plus minus a, also known as e to the 0, which is the identity. So what's this show? This shows that, this is really, really nice. This shows that e to the a inverse is equal to e to the minus a. In other words, e to the a is invertible. Wait a minute, you mean for any matrix, even a non-invertible matrix, if I exponentiate it, it gives me an invertible matrix? Yes. It's hard to be more degenerate than the 0 matrix, right? Look at what the matrix exponential does to the 0 matrix. It turns the 0 matrix into the identity matrix. You can't get much better than that, right? So matrix exponential always takes a matrix and makes it into an invertible matrix. That's really, really nice. That means that the columns of the matrix exponential are linearly independent. Okay. By the way, number 2 is not an entirely easy thing. It's not that hard to prove, but it is a short calculation to really show that. And it's interesting if you let AB equals to AB minus BA, this is called the commutator. Commutator. So if that's 0, that says the matrices commute, right? But if it's non-zero, you actually still have the following formula. E to the a times e to the b is equal to e to the a plus b plus 1/2 the commutator of a and b plus stuff. This formula is known as the Baker-Campbell-Hausdorff relation. I think it has another name in other circles, but it's sometimes called the BCH relation. And like it's what I haven't written is somewhat complicated. It's like commutators of commutators, and then commutators of commutators of commutators, and then Commutators of commutators of commutators of commutators. It's this unending series of nested commutators, which means that if you understand how the commutators work, then you can multiply the exponential of matrices. This red formula actually lies at the heart of a lot of modern physics. See, because the commutators have physical meaning in quantum mechanics. You know, when we look at quantum observables, you have to be able to calculate their commutator. If they commute, that means that they're simultaneously observable. They can be part of a common eigenstate. If they don't commute, that means that there's some sort of uncertainty principle, which means if you know one, you can't know the other precisely. So, I mean, commutators are at the heart of quantum mechanics, but this is also just at the heart of what are called Lie groups and Lie algebras. Anyway, I shut up. So, that's nice. What does this have to do with differential equations, though? I mean, this is great. This seems like a nice accident that we got the solution in the matrix here, but, like, great. So this is an important observation. So we already got half of it already. We have that e to the ta is invertible, right? Which means that the determinant of e to the ta is non-equal to 0. And so what that means is if we look at e to the ta as being, say, x1, x2, xn, then these are linearly independent vector valued functions. So we've already got that the columns of the matrix exponential form a linearly independent set of functions. The question is, are they interesting? Well, let's try it out. What happens if we differentiate the matrix exponential? So what's that look like? That's d dt of I plus ta plus 1/2 t squared a squared 1/3 factorial t cubed a cubed and so forth. So we differentiate term by term. Derivative of the identity matrix, that's a constant matrix, differentiates to 0. Derivative of t times a just gives me a again. This gives me t times a squared. Then I get, what's 3 over 3 factorial? Yeah, it's 1/2 or 1/2 factorial, right? The next thing I haven't written would give us a 1/3 factorial t squared. I'm sorry, that's a t squared, I'm an idiot. T cubed. The power in a is one more than the power of t, right? Because the t gets differentiated, but the a just rides along. So you can factor an a out, right? You factor a out, what do you got? You got a times I plus ta, 1/2 t squared a squared, 1/3 factorial t cubed a cubed. What's that? That's what? Well, a is equal to ai. I is the identity matrix. So I should have an I there because I can't add 1 to a matrix, but I is like 1 for matrices. But it is a matrix. But what's this? That's e to the ta again, right? What does that mean? This means, by the way, this means that the derivative with respect to t of the jth column of a, e to the ta rather, right, is equal to the jth column of a e to the ta, but by linear algebra, that is equal to a times the jth column of e to the ta. This is called the concatenation proposition. So my point to you is this matrix equation, the jth column of e to the ta is a solution to dx dt equals to ax. I'll try to work this again tomorrow. Next class we meet to talk more about solution matrix. A little bit rushed at the moment. I usually spend about 2 minutes doing a certain calculation here. That'll make it make more sense. But I want to emphasize the truth here, which is that e to the ta is formed by linearly independent columns, each of which is a solution to the problem. What does that mean e to the ta is? What is e to the ta to this? It is a fundamental solution matrix. For which a? The a with real eigenvalues, the a with complex eigenvalues, the a which don't have enough eigenvectors, the a's which do have enough eigenvectors, which a? All a. So this method, it gets everything we've done so far. But why, in some sense, why do I still teach you the other method? Like, I'm telling you now, oh, this solves everything. Why don't we just do this? What's that? Right. To actually calculate with this requires a certain amount of finesse. And when we get through that, what we'll learn is that the eigensolutions we already found appear as a special case of this solution technique. So, but I don't know. It seems almost too good to be true that something so natural as just exponentiating the matrix. Because if you look at this just from a sort of formal perspective, remember, how did we solve dy dx equals to ay? You go, for us, we go lambda equals to a, therefore y is equal to c1 e to the ax, right? Or maybe if I make it t, it's even easier to see the analogy here, right? So you're looking at dx dt equals to ax. So what could be more natural than to say that x equals to e to the ta? But this doesn't quite make sense. That's a matrix, right? So the analogy breaks down a little bit. But anyway, so next class I will show you how we extract solutions from the matrix exponential. Thanks, guys.